The same number can be represented in different ways. Write 2 more representations of each of the numbers in the table below by choosing only from the following list. Note, some of the representations may be approximations. So let's look at 6 to the power of minus 2. Well, 6 to the power of minus 2 is the same as 1 over 6 to the power of plus 2, which is 1 over 36. So we have to find 2 numbers from this list here that are either exactly equal to 1 over 36 or close to it. Let's look at 1 over 36 as a decimal. So we have to take 1 and divide it by 36. We get 0.0277 recurring. Now we can see that 0.027 is in the list. Now to 3 decimal places this number is actually 0.028, but 0.027 is close enough. The other number that is close to 6 to the power of minus 2 is 2.8%. 2.8% is 2.8 divided by 100. So we just move the decimal point 2 places to the left, so we get 0.028. 0.028 is actually 6 to the power of minus 2 rounded to 3 decimal places. 81 to the power of a half is the square root of 81. So this number here is the root. The denominator of the fractional power is the root. So we're getting the square root of 81. And that's exactly 9. So we have to find numbers that are close to 9 or equal to 9. 900% is exactly 9. 100% is 1, so 900% is 9 times 1 or 9. The other value that gives us 9 is actually root 3 to the power of 4. Let's look at root 3 to the power of 4. It means root 3 times root 3 times root 3 times root 3. Well, root 3 by root 3 is 3. If we multiply the square root of 3 by itself, we get 3. And over here we have another 3. So root 3 to the power of 4 is just 3 times 3, which is 9. Two to the power of 20 is a very large positive number, so we have to look for very large numbers from this list. So obviously that rules out 1/9, 1 over 62 and 1 over 81. 16 to the power of 5 could be an answer. We just need to test that out. First of all, let's calculate 2 to the power of 20. It's 1,048,576. Let's look at 16 to the power of 5. It's exactly the same. We could have actually shown that 2 to the power of 20 equals 16 to the power of 5 without a calculator by writing 2 to the power of 20 as 2 to the power of 4, which is actually 16. 2 2 is 4, 2 4 is 8, 2 8 is 16. But then raise this number, which is 16, to the power of 5. 2 to the power of 4 to the power of 5 is actually 2 to the power of 20. We just multiply 4 by 5. It's 2 to the 4 by 2 to the 4 by 2 to the 4 by 2 to the 4. What about 2 to the power of 4 multiplied by 2 to the power of 5? Well, the base numbers are the same in each of these terms. The base number is 2. So when we multiply these two terms together, we get a term with the same base 2, but we must add the powers when we multiply. 4 and 5 is 9. So 2 to the 4 by 2 to the 5 is 2 to the power of 9, which is not 2 to the power of 20. Let's look at some of the large numbers that are left here. Now, this number is a large number, 1.05 by 10 to the power of 6. To work this out, we'd move the decimal point 10 places to the right, since we're multiplying 1.05 by 1 million. So what we get is 1050000. So the decimal point was here, and we move it 1, 2, 3, 4, 5, 6 places to the right. So we get 1,050,000. And that's a good approximation to 2 to the power of 20. 2 to the power of 20 is 1,048,576. So these two numbers are very close. You can see that the gap between this number and this number is less than 2,000. So we can use this number as a good approximation. Actually, there is another number that is a good approximation for 2 to the power of 20, and that's this number here. So I'll just explain this. 0.25 to the power of minus 10 is 1 over 0.25 to the power of plus 10. This number is a very large number, because if we raise 0.25 to the power of 10, we will get a number that is much smaller than 0.25. So we're taking 1 and dividing it by a very, very small number. That will give us a very large number. 1 divided by 0.25 to the power of 10. It actually gives us exactly 2 to the power of 20. So we could use as a third option 0.25 to the power of minus 10, which is exactly 2 to the power of 20. As an aside, let's see why 0.25 to the power of minus 10 is exactly equal to 2 to the power of 20. Well, 0.25 to the power of minus 10 is, as we saw already, 1 over 0.25 to the power of plus 10. Let's write 0.25 as a fraction. 0.25 is a quarter. So we have 1 divided by a quarter to the power of 10. We can write this as 1 over 1 to the power of 10 divided by 4 to the power of 10. If we take a fraction and raise it to the power, we can raise the numerator to that power and the denominator to that power. Well, if we take 1 and divide it by a fraction, it's equivalent to 1 multiplied by this fraction inverted. So we invert this fraction. Well, 1 to the power of 10 is just 1. 1 to the power of any number is 1. So we have 1 divided by 1 over 4 to the 10. Well, that's the same as 1 multiplied by 4 to the 10 over 1. So we just invert this fraction here, and we just want this fraction. This works out to 4 to the power of 10. And if we write 4 as 2 to the power of 2, because 2 squared is 4, we get 2 squared to the power of 10. Then we just multiply these powers, and we get 2 to the power of 20. Giving the number line below an appropriate scale, mark the following numbers on it. Now, all of these numbers here are close to 9. The square root of 82 is a little more than 9, because the square root of 81 is equal to 9. 3 pi is a little bit more than 9. To 2 decimal places, pi is 3.14, so 3 times 3.14 is about 9.4. 8.9 is close to 9. 37 divided by 4 is 9 and 1/4, or 9.25. 9.3 by 10 to the 0, well, that's just 9.3, because 10 to the 0 is 1. Any number to the power of 0 is 1. So all of these numbers are close to 9. Actually, they're all between 8 and 10. 8.9 is the only number that's less than 9. The other numbers are between 9 and 10. So we want to apply an appropriate scale here. So first of all, we better get the decimal representations for these numbers. Now I'm going to write each of these numbers to 1 decimal place. If you get the square root of 82, you get this number. So the second place is 5 or more, so we add 1 to the first place, we get 9.1. So I'm going to use each of these squares to represent 1 decimal place. Or you could actually use 2 squares to represent 1 decimal place. That might be even better. We cannot take this to 2 decimal places, because then we would need 100 units along here, along the length of this line, to represent numbers to 2 decimal places, because we could have 100 possibilities. Let's get 3 pi. So we multiply 3 by pi, so use the full representation for pi, and then round. So I'll round this number to 1 place. It's 9.4. Of course, we don't have to do anything for 8.9. We don't have to do anything for 9. 37 divided by 4, well, you can do that without a calculator. That's 9 and 1 over, or 9 1/4. Now we can round this to 9.3. Or we could leave it as 9.2 actually, it doesn't matter, because 0.25 is midway between 0.2 and 0.3, but we'll follow the rounding convention. and round it to 9.3. As a matter of fact, I might write this as exactly 9.25, because if I'm going to use two squares to represent one decimal place, then 0.25 would be easily represented. Like if this is 9.2 and this number is 9.3, then 9.25 is exactly in the middle. So I think I will leave this as it is. But if you write 9.3, that's fine also. Now the last number is exactly 9.3. So the smallest number is 8.9. So I will plot that here somewhere on the left side of this line. Don't plot it too far over here. We need to allow space to the right to fit these numbers. I'll plot it here. (8.9). So this is 8.9. This number is 9. So I'm using two squares to represent a distance of 0.1. Distance between here and here is 0.1. So that's 9. The number 9.1 is going to appear here. That's on our list. 9.25, well, this number is 9.2. This number is 9.3, so 9.25 is here, midway between 9.2 and 9.3. This number here is 9.3. Finally, we have 9.4. Now I haven't shown 0 on this line. Well, 0 would actually be off the page. If you want to show 0, well, you'd have to put 0 somewhere over here and maybe just use each square to represent a distance of 0.1. Then you'll be able to fit everything, including 0. So what I've done is use this distance for 0.1. Let's redo this question using this distance for 0.1. That way we can fit 0 onto our diagram. Let's put 0 here. So we want 8.9. Well, if we use this distance as 0.1, then to get to 1, we have 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, and then 1. And you can see we're a long way from 8.9, so it's not going to be feasible to show 0 on this line. We have to go off this page. We don't want to do that. And 0.1 really is the smallest unit that we should use to accurately represent these numbers on this line. So you can see that it's best not to try and show 0 here.